Welcome back to Electrochemical Engineering. Today I'm going to talk about fuel cell fundamentals. On the left here, I show a fuel cell stack that's composed of many fuel cells, individual fuel cells in series that was used in 1999 in a Honda concept car. On the right, I show a rendering of a modern fuel cell stack, very similar in design, used in the so-called power cells that are being used to power a number of large semi-truck concepts and production vehicles. The fuel cells are, much like many electrochemical systems, devices that operate at many length scales. So there are current collectors, there are catalyst support layers, gas diffusion layers, there are local catalytic structures, in this case, platinum nanoparticles supported on carbon. We'll talk about each level of structure in this course, and we'll talk about how these function, their fundamentals, and their performance parameters. Fundamentally, a fuel cell is any electrochemical device that drives an overall downhill electrochemical reaction involving a fuel and oxygen to generate two products that have lower free energy. This leads to a reaction that you can extract usable work out of. This reaction is identical to the reaction you would write for the combustion of methanol, except in this case, we're doing that combustion reaction separated in space. At the anode of the fuel cell, we're going to oxidize methanol. Methanol will flow in here in this example. We will extract 6 electrons, 6 protons off that methanol to make CO2. The electrons can go through the external circuit, do work in the external load, and return to the cathode. The cathode reaction is typically the reduction of oxygen. It is easy to reduce oxygen. It's a good oxidant. So we can remove substantial free energy from the electrons coming off the anode and still drive the reduction reaction of oxygen at the cathode. Fuel cells can provide increased efficiency compared to combustion engines because they're not thermal devices. What that means is they're not limited by the Carnot efficiency of heat engines. As a thought experiment, I'd like you to start thinking about this fuel cell structure. Here, there's the current collectors. These are metals, typically, or graphite. There are the electrode materials. These electrodes have important structures spanning length scales from sub-nanometer to hundreds of micrometers because it is in this electrode where the reaction takes place. It's typically a porous electrode. We need to get reactants into this porous electrode. We need to get protons out, so it typically has ionic conductor mixed in it. And we also need to get electrons out, so it needs to be electronically conductive. This region is known as a three-phase region because you have the presence of solid, liquid, and gas, typically. There's an anode catalyst layer and a cathode catalyst layer and a membrane that separates the anode and cathode. The membrane is typically a ionomer. That means it's a polymer that has fixed ionic group. Typically, these are sulfonic acid ionomers in acidic proton exchange membrane fuel cells, same types of materials that are used in proton exchange membrane electrolyzers. They have strong acid groups. We'll talk more about the chemistry of these in future lectures, and mobile protons within there. So this is a solid electrolyte. And you don't need a supporting electrolyte, a soluble electrolyte, for these types of devices. We can use our equation, delta G, the free energy of a reaction, equals negative NF, the cell potential, to calculate the voltage output for the methanol oxygen fuel cell. This, remember, U theta is the standard cell potential, and it is related to delta G naught over NF, where N is the number of electrons transferred in the reaction. You can get the total Gibbs free energy of the reaction by looking up the delta G's of formation of each species in the overall balanced chemical equation, just like you did in first year chemistry. Divided by 6 times Faraday's constant, and you get a voltage of 1.21 volts. Notice that this voltage is actually fairly similar to the voltage for a hydrogen oxygen fuel cell, which is 1.23 volts. The thermodynamic voltage for water electrolysis is the same voltage you can get out by recombining water and oxygen. We'll come back to hydrogen fuel cells shortly. You can also, from the same equation, calculate the enthalpy for the methanol reaction at standard conditions. Delta H of formation of the products minus delta H of formation of the reactants. Overall, this reaction is the same reaction as the combustion of methanol. So the overall delta H, whether you do it electrochemically or you do it thermochemically via combustion, is the same. It's useful to consider the first law of thermodynamics when we analyze the electrical work and the efficiency of a fuel cell system. Here's a general block diagram for a fuel cell. We bring in oxidant, typically O2, in fuel. In our previous case, we used the example of methanol, but the fuel might be hydrogen also. The fuel cell can output electrical work. That's the current times the voltage of the fuel cell integrated over time. And it also outputs products and heat. We know that for an open system, the change in enthalpy is given by Q minus W, where Q is the heat and W is the work done by the system. The convention here is that for Q greater than 0, heat transfer is to the system. And for work greater than 0, work is done by the system. Delta G with a cell voltage of U represent the maximal electrical work the fuel cell can do. And that corresponds to a reversible process occurring infinitesimally slow. Any real process will have inefficiencies, and we won't get the full free energy of the chemical reaction because we have to use some of that free energy to drive the various electrode processes: transport, concentration polarization, electrochemical kinetics. The definition of fuel cell efficiency is the electrical work produced by the cell divided by the total free energy available in the reactants. Unlike batteries, fuel cells are not cycled, but have a continuous flow of fuel and oxidant streaming into the fuel cell, giving off free energy, doing electrical work, and leaving as products. This makes them advantageous for applications where you want to use a large amount of energy over a large time, because you can have a small fuel cell with a large tank, and the overall weight and space requirement is dramatically lower, and the cost is dramatically lower than for batteries. This is why fuel cells make a lot more sense, for example, for driving propeller airplanes, for regional transport, for driving long-distance trucking and ships. We can look more specifically at the voltage efficiency of a fuel cell. This is equation 9.2 in Fuller and Harb, your book. Here it's defined as the rate of electrical energy from the cell over the maximum rate of electrical energy over the theoretical rate. That's the electrical power of the cell over the theoretical power. The actual power is current times voltage. And the theoretical power is just the mass flow rate of reactants divided by their molar mass, assuming we're using exact stoichiometric quantities of input reactants, times the delta G for the reaction. So this is just the total free energy that the reaction has available, and the top is the fraction that's extracted as current voltage, as power through the external system. We can simplify this expression here, writing delta G equals negative NFU, the cell potential, and rewriting the mass flow divided by the molar mass, so this is the moles per second flowing into the system, using Faraday's law to recast that as a total current. This bottom piece, really, if you cancel out the NFs, are simply the current times the theoretical maximum voltage you could get if you did the reaction reversibly. The real voltage you get is smaller than that. So the efficiency of a fuel cell is simply the voltage you're running at over the theoretical cell voltage. There are several different types of fuel cells, and they're typically distinguished by the electrolyte used and the fuel consumed. The electrolyte's really important. The electrolyte determines the structure of the electrode. Are you using a solid or liquid electrolyte? Are you using a membrane ionomer? Are you using a hydroxide conducting or proton conducting electrolyte? All these are important. The electrolyte also determines the design of individual cells, how the cells are combined to form a cell stack assembly, as in the pictures I showed you on the front page, and how you control the fuel cell system. Of course, for any electrolyte, we want a very high ionic conductivity. Why do we want a high ionic conductivity? Well, that reduces the ohmic losses of our fuel cell, the free energy losses driving ionic transport through our electrolyte. We also want a low electronic conductivity. If the electrolyte is electronically conductive, there will be a shunt current an electrical current flowing through the electrolyte from the anode to the cathode. Usually, when we think about aqueous electrolytes or Nafion membrane aqueous ionomers, we don't think much about their electrical conductivity. It's very, very small, negligible. But when we start talking about solid oxide fuel cells, high temperature fuel cells that use solid state electrolytes, oxides as electrolytes, the electronic conductivity can be important and it can lead to losses in the cell. The electrolyte also needs to act as a physical barrier, it needs to be free of pinholes and places for transport of reactants and products across the cell, which you want to prevent. The electrolytes also influence the operating temperature, whether you're a high temperature oxygen conducting ceramic. A ceramic is typically a metal oxide, an inorganic, hard, rock-like material. These are called solid oxide fuel cells. You have to heat them up to high temperature. At the cathode for a solid oxide fuel cell, you actually directly reduce oxygen to make 4 electrons, and the oxygen species can actually diffuse through the solid oxide membrane. We'll talk more about this in the upcoming lectures. The other types of fuel cells are more familiar to you, likely the alkaline and acidic fuel cells, where at the cathode you're driving oxygen reduction, either in basic conditions making hydroxide or consuming protons in acidic conditions making water. Notice half cell potentials are different for these two. That's because the standard state is different in base than it is in acid. Notice also that at the anode, we're in both cases driving H2 to water. Notice also that at the anode, in both cases, we are oxidizing H2, but in basic conditions, the standard potential is much less than in acidic conditions. Now, the difference between the anode and cathode potential in both cases is the same, 1.23 volts. So thermodynamically, it doesn't matter if you use an alkaline or acidic electrolyte for a hydrogen-oxygen fuel cell, but it does matter in the types of catalysts and materials you can use. In an alkaline fuel cell, you can use non-precious metals and oxides because they're stable in alkaline conditions. Whereas in an acidic proton exchange membrane fuel cell, you can only use typically platinum catalysts or platinum alloy catalysts. If you go to the high temperature oxygen conducting ceramic fuel cells, these operate typically at 500 degrees Celsius or higher. And in this case, the catalysts aren't even that important. You can use things like nickel, ceramide. Ceramide is a ceramic metallic composite for the electrode, and it has very fast oxygen reduction kinetics because you're at such elevated temperature. There's lots of energy for your electrons to get over the charge transfer activation energy at the electrified interface. Here's a table from your book, table 9.1, that highlights the applications, temperature range, and details about different types of fuel cell technologies. There's a so-called direct methanol fuel cell. It works in low temperature and uses the same membrane as a proton exchange membrane hydrogen-oxygen fuel cell. The proton exchange membrane fuel cells, they're the predominant commercial fuel cell. They are very well developed. They use platinum as catalyst for oxygen reduction and hydrogen oxidation. They're used in buses, automobiles, portable power, including anticipated use in airplanes and things like that. They have a lot of advantages, but they do require precious metals. Alkaline fuel cells require pure hydrogen and oxygen usually, and that's because the CO2 will react with hydroxide and neutralize it. CO2 is a weak acid. It reacts with hydroxide to make carbonate, but it does allow the use of non-precious metal catalysts. But you can't feed it just air at the cathode where oxygen reduction is occurring. You have to feed it pure oxygen or air purified from CO2 species. Phosphoric acid fuel cells are used at intermediate temperatures in some applications. And then the high temperature fuel cells span sort of molten carbonate technologies and solid oxide fuel cell technologies, which we talked about. The challenge with the solid oxide fuel cells is that operating at these very high temperatures limits the materials availability and makes actually building the fuel cell very expensive. So the capital expense of building these ceramic-based fuel cells is much higher than the simple proton exchange membrane fuel cells. But all these technologies have important applications, and there's important research to be done to improve them. Let's take a moment now to think about the polarization curve for a fuel cell. A polarization curve, whenever you see this, polarization, what does that make you think of? Makes you think of polarizing an electrode, changing the voltage across our device and measuring the current, or vice versa, changing the current and measuring the potential. So a polarization curve is the relationship between potential and current. Here are three example polarization curves for an alkaline fuel cell here, a proton exchange membrane fuel cell here, and a solid oxide fuel cell here. Notice these three curves are very different. What I want you to do, and we'll do this in our in-class work, is think about why these three curves look so different. What explains the different shapes of these curves based on a microscopic picture of what's happening in these different fuel cell technologies? Let's talk about them a little bit generally, though. If I go to zero current, I'm measuring the open circuit potential of the fuel cell. That's determined by thermodynamics primarily. It's determined by the free energy available to do work. At zero current, I'm not driving current through the electrode reactions, so the kinetic overpotentials, the transport overpotentials, those go to zero. Now it turns out that the open circuit potential doesn't always match the thermodynamic potential if there's internal crossover, internal current flowing at open circuit. We'll talk about that in a moment. But primarily it's determined by the thermodynamics of the cell. Now, when you start polarizing away from zero current, when you start passing current through this cell, you often see this exponential type shape. Notice I'm increasing voltage here, increasing overpotential, and the overpotential here is actually a negative value because I'm driving current through the cell, which is consuming some of the free energy I had available from the cell reaction. So the net voltage I get out of the cell decreases as I start increasing current. And notice that the current starts to increase exponentially as I start using more and more of my free energy to drive the reaction. We call this the kinetic regime. Why is that? Well, Butler-Volmer type behavior or Tafel behavior, we'll talk more about that in the coming slides, predicts that the current increases as the exponent of the overpotential. But at some point, the kinetics have become sufficiently fast that driving additional current via the Tafel expression doesn't take that much additional free energy driving force. Now we get into a regime which we call the ohmic regime, where the current voltage response is approximately linear. That's because the dominating factor consuming free energy over this range is driving the ohmic transport of species, either electrons, but usually ions, through the membrane and the ionomer catalyst layer between the anode and cathode. The ohmic voltage drop, V ohmic, equals the ohmic resistance times the current. So it grows linearly with the current. At some point, this curve starts to curve. At some point, the voltage takes a dramatic turn down. So we get dramatically less voltage if we try to push the current even higher. This is what we call the mass transfer limited regime. At some point, you literally run out of reactants to react at your anode and cathode. That limits the maximum amount of current, no matter how much free energy from the cell reaction you're willing to spend driving the reaction through the cell. Each of these technologies are different, and you can think about why these different processes limit the technologies in different ways. Understanding this plot is going to be very important for your understanding of fuel cell and many electrochemical systems. So I encourage you to spend some time making sure you understand very well exactly the meaning of the open circuit voltage, the kinetic curved part of the cell, the linear part, and the mass transfer limited component of the polarization curve. Here's a more explicit breakdown. The kinetic region is usually governed by the Tafel equation. Here's the exponent type behavior. The ohmic region is the linear portion of the graph. It's governed by the resistance, i.e. the thickness and conductivity of the electrolyte. And then the mass transfer region is a nonlinear portion of a graph that occurs at the highest current densities. It's governed by the transfer of reactants to the electrode. Let's go back and consider now the thermodynamics of the cell. The open circuit potential or open circuit voltage, OCV or sometimes OCP, is when the current density is zero. What is the voltage difference, the difference in free energy of the electrons at the anode versus the cathode? Temperature affects this equilibrium open circuit potential, and we know that delta G equals H minus T delta S. So if I take the derivative of the free energy with respect to temperature, I see that it's equal to negative S. So the entropy of the reaction governs the temperature dependence of the cell voltage. Here's some data showing the equilibrium potential as a function of temperature. You can see that here. Now, it turns out that it's a little bit more complicated than that because entropy itself has some temperature dependence, which you can work out, and I'll show you on the next slide. So you have a sense of how big an effect this is. At 80 degrees Celsius, an H2O2 fuel cell has an open circuit voltage of about 1.17 volts. If you run that same reaction at 800 degrees Celsius, the open circuit potential is less than 1 volt. So it's substantially less. So the difference can be substantial. This is bad from the perspective of getting the maximum electrical work out of this reaction. From the prospect of running the reaction the other direction, though, if you were looking to make an electrolyzer that split water into hydrogen and oxygen, then this voltage lowering would allow you to put in less electrical work and get more of your energy needs from thermal energy to drive the reaction forward. This is a derivation of the temperature dependence of the cell potential, and you can see how this is done if you're interested. Let's take an example. The solid oxide fuel cell has an open circuit potential from figure 9.3 in the previous slide of about 1.1 volts. This is actually larger than the OCV calculated using equation 9.3 of about 0.979 volts. Why is this? Well, it turns out we also have to consider the gas composition. Remember, the cell potential is the standard cell potential, equilibrium standard cell potential, plus these activity terms. And we need to consider the activity of hydrogen, water, and oxygen. The activity of each gas is taken as the gas partial pressure. For an SOFC, the anode gas is largely hydrogen with a little bit of water to keep it humidified, and the cathode is pure oxygen. If you plug in for these values, you find a voltage of 1.1 volts. So the thermodynamic voltage is, of course, the standard voltage plus the correction for the non-unity activities, for not being necessarily at standard state. Now let's think about an alkaline fuel cell. With pure oxygen, the mole fractions of water, hydrogen, and oxygen are all about 0.5. That is, you usually feed humidified oxygen and humidified hydrogen to both the anode and the cathode. So the feed is about half oxygen to the cathode and about half hydrogen to the anode. We can now calculate the cell potential based on the standard state potential and correction for the activity terms. We can now calculate the cell potential based on the standard state cell potential and correction for the activity terms. We get about 1.17. Now, in the figure 9.3, the data shows us open circuit potential about 1.05 volts. Why is it so much lower? Well, the reduced value is due to the permeation of oxygen and hydrogen across the separator. And this is acting as a backwards recombination current, a chemical current flowing through the fuel cell that is working to equilibrate the anode and cathode and drawing down the potential from the theoretical limit to the measured value. In a proton exchange membrane fuel cell, typically again use about 50 mole percent water vapor. You can plug these in to the expression here and get the theoretical open circuit voltage at 80 degrees Celsius. Again, we have about 0.95 volts compared to 1.16 volts in our real system versus our theoretical system. So why are these so different? Well, we talked about the permeation of reactants across the electrolyte. This is sort of an internal shunt current trying to pull those voltages into equilibrium with each other, right? That's what the crossover currents are going to do. And the sluggishness of the oxygen reduction reaction in acid at low temperatures is also important. What that means is essentially the electrode potential at the cathode is set by the equilibrium of those electrons in the cathode with the electrons in oxygen. It relies on the kinetics being fast enough to set the electrochemical potential of the electrons. If there's other impurities that compete with setting that equilibrium potential, it can be hard to measure the full open circuit potential predicted by thermodynamics. Now let's talk about kinetics. We can evaluate the fuel cell polarization data on a Tafel plot, where we plot the potential now versus the log of the current density. You'll notice this stretches out the low current density data. If you look at this low current density data here, the open circles, and you correct for the ohmic resistance, so we're going to add back the potential that we lost due to the ohmic resistance, I times R ohmic, then you can see there's a large region over which the simple Tafel equation holds. How do we know that the Tafel equation is holding over this region? Well, the plot is linear on a semi-log scale. So the current is increasing logarithmically as I move from left to right on this plot, and the potential is only decreasing linearly. So a small change in potential is giving rise to a large change in current. This is the definition of the Tafel behavior. Can typically fit this data with a transfer coefficient of 1. You can solve for the Tafel slope from the Tafel expression, and it's equal to the natural log of 10 times RT over the transfer coefficient times Faraday's constant F. Here's the numerical evaluation, and you get about 70 millivolts per decade at this elevated temperature. Remember, it was about 59 millivolts per decade at room temperature. One interesting thing to consider is, why is this transfer coefficient 1? Typically, phenomenologically, one interesting thing to consider is, why is this transfer coefficient 1? Usually we said the transfer coefficient varies from 0 to 1, but is rarely physical for have a transfer coefficient of 1. Well, if you remember, that was for an elementary step. That was for the symmetry factor describing a single electron train. This is describing actually a much more complex reaction. It's describing primarily the 4-electron reduction of oxygen, which has the slowest kinetics in the entire fuel cell. The hydrogen oxidation reaction kinetics are substantially faster and don't contribute substantially to the kinetic overpotential. The reason the transfer coefficient is about 1 is because this is what is found experimentally. There's no good theory to explain this rigorously as far as I know. It's essentially a fitting parameter to the data. When we're analyzing fuel cell data at low current density, we know that the ohmic and mass transfer polarizations or overpotentials are small. This is because those typically go more linear with applied current, so they go to 0 as the current approaches 0. At these low currents, the cell potential is dominated by reaction kinetics. So whenever you see strong curvature at low current densities, you can interpret that usually due to sluggish reaction kinetics at one of the electrodes. In the alkaline fuel cell, compared to the proton exchange membrane fuel cell, the O2 reduction reaction kinetics are faster. So the curved portion at lower current density is smaller. Let's go take a look at the data we showed earlier. The alkaline fuel cell is here, whereas the PEM fuel cell is here, proton exchange membrane. Notice the PEM's fuel cell has a very large exponential region and a large kinetic loss, whereas the alkaline membrane fuel cell has a smaller kinetic loss. For the solid oxide fuel cell, the temperature is much higher, so the oxygen reduction overpotential is much less important than in low temperature fuel cells. We can again see how that manifests in the data, and what you see is the current voltage polarization curve has very little exponential regime, and in fact, it seems to be ohmic limited down to very small currents. There's very little kinetic regime for a solid oxide fuel cell. But you'll notice the slope is much steeper, indicating that the ohmic losses are much larger in a solid oxide fuel cell due to the lower conductivity, at least in this example, of the ceramic electrolytes compared to the low temperature polymer ionomer electrolytes used in proton exchange membrane fuel cells. You might think a little bit about the process of oxidizing H2 at the anode and why we haven't been talking about that much in this presentation. It's useful to think about how the kinetics, the current, depend on the partial pressures of the reactants. This is from illustration 9.2 in Fuller and Hart. The oxygen reduction kinetics are usually described by a Tafel equation. That's this exponential dependence on the overpotential, so the voltage driving the reaction relative to the equilibrium potential. This is the overpotential. And is considered to be first order in oxygen partial pressure. So the pressure of oxygen is a prefactor that affects the current you measure as a function of the exchange current and the driving force dependent Tafel part. P reference is a reference pressure, typically the standard state pressure of your system. In this problem, you can estimate the change potential for a 1 decade change in current density. 1 decade is an order of magnitude change in current density, assuming that the fuel cell is operating in the kinetic regime. That means that the system is purely controlled by kinetics and no other overpotentials are substantially adding to the voltage loss. We can write the Tafel equation for two currents, I1 and I2, and simplify to this expression. Notice if the partial pressures are the same, those cancel out as well as I naught in the ratio. We can calculate delta V and find for a 10-fold change in the current, we get a 59 millivolt change in the voltage output from the cell. This is exactly equivalent to the Tafel slope calculation earlier. This one is operating at 25 degrees C, which is why it's 59 millivolts per decade. Earlier, we did an example that was operating at higher temperature. So the millivolts per decade, the Tafel slope, changes. Let's now talk about the ohmic region. Ohmic losses increase linearly with current. This comes simply from Ohm's law. V equals IR. So V ohmic, the ohmic loss, or eta ohmic, the ohmic overpotential, is I, the current running through the cell, times the ohmic resistance. This linear slope, i.e. the ohmic resistance, you can calculate from the slope of the current voltage curve. If I give you a current voltage curve for a fuel cell, you should be able to extrapolate and calculate the ohmic resistance. The slope is just the change in voltage over change in current. That's approximately equal to the length of the electrolyte divided by the electrolyte conductivity, or the ohmic areal resistance of the electrolyzer, or fuel cell in this case. This ohmic resistance typically has units here, not of ohms, but of ohms times area. It's an areal resistance. Why is this? Well, the actual resistance is for a specific device of a specific geometry. We need to know the area of our device in order to calculate its actual resistance. So we have this area normalized resistance. To get the actual resistance, I need to divide this by the area, here in meters squared, such that larger areas, of course, have lower resistances because they can more easily pass ionic current. Just like a bigger wire has a lower resistance to electrical current. Now let's talk a little bit more about mass transfer. Mass transfer describes the transport of reactants and products to and from catalytic sites by diffusion and fluid motion. Fluid being often two-phase flow of liquid and gas, or could just be gas or liquid flow, depending on the system. The mass transfer efficiency is really related to the current flowing through the cell. When you're driving higher currents, the voltage driving the mass transfer, creating those diffusion gradients that are transporting the species from the incoming stream to locally where the reaction actually takes place, take more free energy to set up. Just so you have some terminology down, when we talk about things like cathode polarizations, we're typically talking about the kinetics of doing O2 reduction at the cathode. When we talk about mass transfer at the cathode, we're talking about O2 diffusion to and from the cathode. Whenever we hear the word ohmic, typically we're talking about ion movement within the electrolyte, though it could also be in part due to the electron movement in the wires and catalytic layers of the fuel cell structure. I'll also point out we're typically talking about cathode polarizations and oxygen diffusion. Of course, anode polarizations exist too. You might think about why the transport of hydrogen and the polarization due to the kinetics of hydrogen oxidation are faster than for O2. And remember, each of these processes is activated, so they're all affected by temperature. Here's an example from a proton exchange membrane fuel cell and a solid oxide fuel cell. The total voltages, thermodynamic voltages, are given by the height of these boxes, and the various losses are shown by these gray boxes, whereas the light gray box tells you the fraction of the free energy, the fraction of the voltage that you're getting out of the fuel cell in this example. In a solid oxide fuel cell, the polarization losses are small. They're small because you're operating at high temperature. But the ohmic losses are large because the solid is not as good of an electrolyte, typically, as the ionomer membranes. At the low temperature fuel cells, low temperature meaning below 100 degrees Celsius, the cathode polarization is one of the main losses, depending on the current density you run at. Now let's talk about the maximum power and the operating conditions. The total cell voltage is the open circuit theoretical potential minus the ohmic losses of driving current through the cell, minus the anode kinetics, minus the cathode kinetic overpotential, minus the concentration overpotential at the anode and the concentration overpotential at the cathode. Remember, concentration overpotentials are due to the diffusion gradients that the system must set up. There are a number of important variables that affect this: temperature and reactant composition, i.e. the partial pressure of the gases. And generally, as the temperature goes up, the overpotentials go down. Let's talk about ohmic losses. Temperature has a big effect on the conductivity of electrolyte. Why is that? Well, typically in electrolytes, you have ions, and the ions are diffusing around via random hopping. And each hop has an activation barrier to get from one location to another location. Y-axis here is energy, and this might be position. As we increase temperature, we increase the available thermal energy to get over that activation barrier. And therefore, the conductivity increases exponentially with temperature. Pressure, on the other hand, has a negligible effect on ion conduction. For the kinetic overpotential, temperature affects the exchange current density, the equilibrium potential, and the exponential term in the Butler-Volmer equation. Temperature might also cause the reaction mechanism to change. The temperature effects on the exchange current density, I naught, are given by equation 3.18 in Fuller and Haar, and also shown in Bard and Faulkner, the text we used earlier in this series of courses. Typically, the exchange current density is given by a prefactor times this exponential term as the activation energy over RT. As temperature increases, this exponential term gets larger. Pressure also affects the kinetic overpotential, and these effects manifest in the exchange current density. We can write the exchange current density, that's the facility of the reaction going forward and reverse at equilibrium, in terms of a reference exchange current density under standard conditions or some reference state condition, and the ratio of the concentrations of all the species involved in the reaction under experimental conditions and reference conditions. Much like you learned about in freshman chemistry, we raise these ratios of concentrations to a power, which we call the order of that particular reactant in the rate expression. These orders, gamma 1, gamma 2, etc., need to be determined experimentally. You typically can't easily predict them. So, for example, when we say a reaction is first order in one component, say O2, this might be the partial pressure of O2 here, divided by some reference pressure of O2. When we say it's first order in O2, gamma 1 would be 1. If it was second order, it would be 2. Let's consider now the concentration polarization. This is the voltage required to maintain a concentration gradient driving the transport of our reactants to where they are consumed. We can write the limiting current density just like we did in Bard and Faulkner chapter 1. It's related to the distance, the thickness of the diffusion layer. We called that the stagnant layer last term in Barden-Faulkner Chapter 1. It's related to the diffusion coefficient of the species, the concentration of the species, and n, the number of electrons transferred, and Faraday's constant. This is essentially Fick's first law, governing flow due to diffusion. The concentration at the edge of the diffusion layer is set by the bulk concentration, the partial pressure of O2 in the incoming gas stream. The concentration at the electrode surface, or in a three-dimensional electrode, it's very complicated, but at the edge of the other edge of the diffusion layer is zero. All the oxygen is immediately consumed. And so the flux of oxygen, in this case, is maximum when that gradient goes from the bulk concentration to zero at the electrode surface. You might also note that as you increase temperature, the gas concentration is pressure over RT based on ideal gas law, is proportional to 1 over T. So the concentration actually goes down with temperature, but the diffusivity goes up with temperature. And so there's a net small increase in the limiting current as you increase temperature, but it's not as much of an increase as you predict just by changes in the diffusion coefficient. Now we can think about calculating the maximum power from a fuel cell. Remember that power is simply current times voltage. It has units. What are the units of power? Well, the units of voltage is volts. The units of current is coulombs per second. So this has units of coulombs times volts per second, which is equal to joules per second, which is equal to watts. So the unit of power is, of course, a watt, like a 100-watt light bulb, for example. What we want to do is we want to figure out where is a fuel cell going to have the maximum power. Remember that current and voltage are not independent, so I can't simultaneously maximize current and voltage. As I increase the current, the voltage I get, the free energy per electron, goes down. And that's due to polarization losses, including kinetics, concentration, and ohmic overpotentials. Now, when I equals 0, the power is 0. And when the current is so high that all the equilibrium voltage is needed to drive the current, then the voltage is 0. So we expect the power to be 0 both at very low current, approaching its 0 current, and at high current. And somewhere in the middle, it's going to be maximized. How do we maximize the power? Well, the differential cell resistance is determined by the slope of the IV curve. All other losses are grouped as eta other and assumed to be constant. So what we can do is we can say the voltage is approximately the cell voltage minus the other losses. These are the kinetic losses, which you're going to assume are essentially constant after the kinetic activation regime, the low current regime, minus I times the ohmic potential. So we can estimate the voltage. So we can estimate the voltage we get out of the cell as a function of current this way, and plug into the expression for power equals voltage times current. Now we have an expression in terms of the equilibrium potential, the other overpotentials, which remember are the grouped kinetic and concentration overpotentials, which are typically relatively constant in the ohmic middle region of a current voltage polarization curve. This is sort of the ohmic region is sort of here. And so those kinetic losses have already been paid, and increasing the current in this region is mostly dominated by resistive losses. So if you imagine now, we're going to get a plot of power versus current that looks something like this. There's going to be some optimal current to run at to get the maximum power out of our cell. To find this, of course, we take the function we derived for the power, and we take the first derivative and set it to 0, and solve for the voltage at the maximum power. We can use the voltage at the maximum power to calculate the current at the maximum power. We can plug both those terms into the expression for power, and now have a full expression for the maximum power this cell will put out. As you can see, having low electrolyte resistance is the most important for high power from a fuel cell. Here's some actual data from Bill Mustaine's group at South Carolina, one of the, world leaders in alkaline membrane fuel cells. It's a very nice results where they've been able to get very high power densities for an alkaline membrane system, here about 1.4 watts per centimeter squared. At a current density, remarkable current density of 3.5 amps per centimeter squared. And I encourage you, if you're interested in these types of technologies, to read this review paper on the subject. We'll talk more about this in our in-class work. So that's all I have for you today, and I'm looking forward to chatting with you soon.